Alright, welcome to lesson 2.2, linear functions and models. Okay, some basic facts. Recall that a linear function is a function that has the form f of x equals mx plus b. In other words, y equals mx plus b. Second fact, the graph of a linear function is, of course, a line, a straight line, right? The slope of a linear function is your m, okay? So the slope of a line is your m. And there's a formula for it. You can take any two data points and find the difference in y's over the difference in x's. So we sometimes call this the rise over the run. So remember that the rise are the y's, or the y's are the rise. A convenient way to find the equation of a line is to start with y minus y1 equals m times x minus x1. This has proven to me to be the fastest way to begin working with this equation of a line if I seek to find it. And this is called the point slope form of a line. Okay? If you're given two data points, x1 and x1, y1 and x2, y2 only, then there is exactly one line that passes through them, right? Think about it. If you have 2 points, there's only one possible straight line that can connect them. On the other hand, if you're given, let's say, more than 2 points, and you'll notice that they're not all on the same line, then you can find what we call a line of best fit. A line of best fit for those points. So what we're talking about here in this last fact is if you're given a set of data that appears to form a linear pattern like this looks to me like a rising group of points, and they seem to be forming sort of a straight line pattern there. That red line I just drew is the line perhaps that would best match the data. Notice that this line doesn't necessarily touch all the points, or even many of them at all, but it does its best to pass through these. Okay? Alright, let's look at some examples here. Consider a linear function f of x that passes through the 2 points 2, 1, and 3, 4. Find the slope of the line. So that's going to be a pretty easy problem because we have a formula for that. If we treat this as x1 and y1 and this is x2 and y2, we can simply do 4 minus 1 over 3 minus 2. So this is giving us 3 over 1, or just plain 3. Finding the equation of the line, I said a moment ago that a convenient way to start that is to go ahead and use y minus y1 equals m times x minus x1. We already were given x1 and y1 in the beginning. They were 2 and 1. So we can just write y minus 1 equals m times x minus 2. As for the m, we found that back in the previous problem. It was 3, right? So we can steal that and use it. Now you're welcome to leave your answer this way, although most teachers won't allow it. What you want to do for most teachers is distribute the 3 and then isolate the y. So I'll go ahead and do that as well. But if you go ahead and distribute the 3, you get 3x minus 6. And the left side is y minus 1. You could add that 1 over to the right. So the final answer is y equals 3x minus 5. And maybe you remember this form of the answer is called the slope-intercept form. Slope-intercept form. So this first one is point slope. The second one is slope-intercept. Okay? Now that we have put it into slope-intercept form, the 5 that you see here is conveniently the answer to the next question. So this 5, this negative 5 I mean, is the answer to the next question. So the answer to this is simply the y-intercept is y equals negative 5. Okay? Alright. The x-intercept of the line can be found simply by making your y 0. So set y equal to 0. So you go 0 equals 3x minus 5, and then you solve it. So you add the 5 over and divide by 3. Looks like x is 5/3. It's very common to get fractions, right? I mean, if you're going to get a nice clean y-intercept like negative 5, don't be surprised that your x-intercept is not a nice number. Most of the time, you get fractions for everything. So Quick comment on the previous problem. So we just finished the x-intercept. The y-intercept of the line could also be found by making x 0. So basically what I'm saying is you could just, or let x equal 0. So when it says 3x minus 5, just plug in, literally plug in 0 for your x, and then you're left with the answer. So it's just negative 5. Like we said, it's negative 5. Okay, next says find the value of f of 10. So you might say, well, where's f? I don't have f. Well, remember, y is 3x minus 5. Written as a linear function, we would call it f of x equals 3x minus 5. Okay? So here is the linear function. It's written as f of x format, you know. And so to find f of 10 literally just means to let your x be 10 and see what happens. So we let our x be 10, and we get 30 minus 5, 25. Okay, and I'm going to add one more slight question to this one. If f of x is equal to 2, find x. Okay, so this is a different question entirely, as you can see. And what it's really asking for is, if y is 2, can you find what x is? So it's actually kind of a reverse sort of thing. And so I'm going to go ahead now and let the left side be 2. The right side is still 3x minus 5. And we're going to isolate x this time. So we're going to add the 5 over. And we get x equals 7/3. All right, and there you have it. Next example. Consider an object that increases its value each year. Suppose that the object is purchased for $2,400 and is worth $3,000 after 5 years. The instructions tell us to plot the data given with time on the x-axis and the value in dollars on the y-axis, and then to graph the linear function that passes through these points. Okay, so let me give myself a little room to work that out. Okay, so it doesn't have to be a beautiful graph, okay? What we're saying here is just simply that we have a x-axis that's years and a y-axis that's in dollars. And we already know that when we first bought this, that would be at 0 years, so t equals 0. The object was $2,400. So we can assume that 0 is our number of years and $2,400 is our value. And that is the point 0, 2,400. So that would maybe go, maybe we can break this y-axis down by thousands. So 10 to 1, 2, 3, 4, 5, 6, 7. So this is 7,000 at the top. This is 1,000 at the bottom. And it starts with a value of 2,400. So that would just be, you know, right between, you know, 2,000 and 3,000. So right about there. And we also know that if you wait 5 years, so t is equal to 5, it's worth $3,000. So let's mark the x-axis using units of 1, 2, 3, 4, 5. So it's only risen, you know, $600 in value over the years, and that's over a 5-year span. Okay? So here's your line. They asked us to go ahead and oh, that's way too thick. Our line asks us to draw that, so let's make it much, much thinner. So this line is rising, and this is what they were saying. How do we know it's a straight line? They actually said in the instructions that it is linearly increasing. So watch for that word, linearly increasing. Okay, so it's straight line is what it means. Okay, so the next thing we're going to do is to find the function v of t, where v is the value in dollars, and t is the number of years since the object was purchased. Okay, so let's get started on that. I'll give myself a little bit more space there too. Okay, so we can use the idea that y minus y1 is equal to m times x minus x1. We're not really using x and y, we're using t and v of t. So our variables are t and v of t. Those are like your x and your y. So instead of writing y minus y1 equals m times x minus x1, I'm going to write v of t minus v of t1 equals m times t minus t1. So I'm replacing all my x's with t's and all my y's with v of t's. So please pause it and pay attention to the notation if you so need to do that, okay? All right, to get the m, we'll do the same thing we did last time. So m is going to be the slope of this line. We already have the endpoints. The endpoints, remember, were 0, 2400 and 5, 3000. So we got that back in part A. Right? Okay, so now we're going to find that slope. Let's do 3000 minus 2400. Sorry about that interruption. Okay, so we're going to do 3000 minus 2400 over 5 minus 0. And this gives us 600 over 5, or you could say 120. Let's put units on that, just so we understand it. That is a number of dollars that it has increased by over a 5-year span. So the units on this would be dollars per year. So it went up $120 each year. It did that for 5 years. That increased it $600. All right, now let's take this stuff, move it over a little bit. That's our slope, you see, it's 120. So let's go back now and fill this in. So we have v of t minus, and then we just found this slope was 120 times t minus. Now as for the t1 and the v of t1, we can use either data point. I suggest we use the 2400 and the 0. So the 2400 and the 0, stealing that from this point right here. So you're just going to use either the 0, 2400 or the 5, 3000. I'm voting on the first one. Okay? So let's put in the 2400 for the y, the 0 for the x, and then we're going to isolate v of t. Okay? So the function is going to be 120t, because this 0 doesn't really count, right? Just cross it out. 120t, and you're adding that 2400 over to the other side. So here is our linear function. Okay, so what's cool about this is, well, first of all, let me say this. This is called a model. Okay, this is called a model. What you created is the model, or the linear model. This function will help us to predict other values on different years. So what we can do now is estimate the value, for example, after 6 years have passed. Whoops. Okay, so now that we have the model, we can just simply use it. So we're trying to find the value after 6 years. Mathematically, we write that as v of 6. That's a positive 6. V of 6. So we're just going to do 120 times 6 plus 2400. In other words, 720 plus 2400. In other words, 3120. This is a dollar amounts. It's a value, so you should give it units, especially on a word problem, a story problem. Okay, that's a pretty easy step there, but pause it and rewind it if you didn't catch it all. Okay? All right, let's look at our next question regarding this value problem. So, how many years must pass by before the object is worth $10,000? So what you're looking at here is a desired worth. So this is a y value, actually. This is like our output value. That would actually go on the left, like this, 10,000. And this is equal to 120 times some mystery year plus 2400. So our goal is to set the function itself equal to 10,000 and solve. Subtracting, we get 7,600 equals 120t. And dividing, we get 6.230 when you round to the nearest thousandth of a year. Notice this is a time. So basically, we have to wait about 6¼ years for the value to reach $10,000. So I'm not sure what this thing is. Maybe it's a classic car, and it's really raising its value. Although I don't really know. I don't know much about cars, but this seems to be like it's never going to stop growing, right? However realistic that is, that doesn't matter to me too much. What's important on this problem is just the fact that this linear function, we can model it and make predictions about its value, or when its value will be certain values. Okay? Next problem. Okay, now I grew up in Taiwan, so I haven't really announced that to the class yet, but those watching the video will know. And it was a humid place to live. So I went online and I found a humidity chart for Taiwan. Okay? I'm not sure which year this is. I got this from taiwan.climatetemps.com. But these are the average temperature and relative humidity for the months January through September. There's a reason why I didn't include October, November, and December, okay? But I'm not going to mention it right now. So we're just going to use this data. Now, what happens when we try to study this data? Well, we notice, first of all, that if you plot it, it does increase if you're doing relative humidity versus average temperature. If you're doing average temperature versus relative humidity, you can see the relative humidities really don't increase much. In fact, they kind of go down and up and down and up. So we have to decide which axis we want to be our y-axis. So we're going to go ahead, and I probably should have typed this, but we're going to use any two data points in the table, and we're going to find a linear function, and we're going to let our linear function be a linear function for temperature, okay? So linear function for temperature. I probably should have typed that in the first place, okay? All right, so let's see what that would look like. So we know first that we'll need a slope, right? So m will be. And since we're doing temperature as our y, because the function will be a temperature function, that means y for the temperatures, we're going to go ahead and pick any 2 months. So why don't we pick let's pick August and June, okay? So this is like x1 and x2, this is y1, this is y1 and y2. You might say, Mr., why do you have the y column first? And it's because they're telling me to find a function for temperature. So the temperature column, that's the first column here. Let me scroll up and show you. This is the temperature column, right? So that has to be our y column. We don't have a choice. Okay. So this is our dependent variable. So we're going to do 28 minus 26.5 over 78 minus 81. This gives me 1.5 degrees Celsius over 3 months. I'm sorry, over, what am I saying? Over 3%. So this gives us 0.5, and the units are funky. It's degrees Celsius per percent relative humidity. Okay, so don't stress out too much about units. Why don't we just put 0.5, okay? We'll just put 0.5, and let's write our function as best we can. So we know it's a temperature function, so it's going to be T minus T at humidity 1 equals m times humidity minus humidity 1. So this is the same thing, folks, as y minus y1 equals m times x minus x1, but I'm using h instead of x because h represents humidity, and I'm using t instead of y because temperature is my y coordinate. And now I'm going to go ahead and plug in my values. So t is supposed to be my function. In fact, I'll call it t of h. So t of h minus, and let's just use the month of August here. So I'll put in the 28 here, equals, and then m times humidity, so h, that's an h, believe it or not, h minus the 78% humidity. And then the m we found earlier, that's the 0.5, so we'll steal that and stick it in right here. Okay, so we basically get t of h minus 28 equals 0.5 times h minus 78. And if you go ahead and distribute and put this into function form, we'll move the 28 over in a minute, we get 0.5 h minus 39, and if you add this 28 to both sides, let me do that in black. If you add the 28 to both sides, you get the temperature as a function of humidity is 0.5 times the humidity minus 11. Okay? This is the function they were talking about. Now here's the problem. If you actually graph this data from Taiwan and you look at it, and then you graph the line that I said we should graph, this 0.5h minus 11, they may or may not look like the same graph. Okay? So this is time to get out our calculator and see how well Mr. Shore's little model works. Okay? So let's see here. Whoops, where'd it go? Well, let me find. Okay, so I got my calculator open, and I pulled up my table, and remember I was going to make my left column my y's and my right column my x's. So what I'm going to do is I'm going to go to Stat, and I'm going to go to Edit, and I'm going to type in the 84, the 84, the 84, the 83, the 82, the 81, the 78, there's two 78s, here, put those in, almost typed 87, and an 80, going to go back up and double check that I typed that right. So it's 84, 84, 84, 83, 82, 81, and then I have 78, 78, 80. Those are my x's. My y's are 15.5 and 15, and 16.5 and 20.5, and 24 and 26.5 and 28.5 and 28 and 26. Let me just double check that I typed those in correctly. 15.5, 15, 16.5, 20.5, 24, 26.5, 28.5, 28, and 26. Okay. Now, what's really cool about this calculator is you can study these data points. Okay, you can plot them, you can do all sorts of things. But let's see how it looks when we graph it. So I'm going to go to Zoom. I'm going to go to Stat Plot first, and I'm going to make sure it's turned on. Okay, so I press Stat Plot, that's second, and y equals, and I'm going to turn it on. Now, plot 1 is going to be a scatter plot. So you can see I've selected, it was actually default selected, the graph that just contains a bunch of dots for data. For X list and Y list, I want to use lists 1 and list 2. Okay, if you want to change these, you can, but remember your table was set up, remember your table titled L1 and L2, so I don't know why you'd want to change it, okay, which you can if you want to. So let me go back to stat plot. To change it, by the way, you have to use second, and then down here you'll see L1, L2, L3 at the bottom, okay, along with L4, L5, and L6 if you have more data. But I'm going to use L1, L2, and I like this standard little box mark, so I'm going to leave that as mark. Now I'm going to press zoom. Oops, first I'm going to press graph, and then I'm going to press, let me quit out of here first. I'm going to press graph, and you won't see much, it's because the data's off the screen, but if I do a zoom stat, so I'm just kind of scrolling around here in the zoom menu, zoom stat right there, it will try to fit my data. So what you're looking at here on the x-axis are humidities, and on the y-axis is temperatures, and these points are scattered along like so. They might say, Mr. Shore, that does not look like a straight line. I agree. And now I'm going to graph the line that I had come up with. Negative, it was 0.5h minus 11. Oh, and Mr. Shore made an error. I just caught it here. There's a negative. You probably caught this already. There's a negative there, and there's a negative there. So that means there's a few mistakes down further in the work. My bad. There's a negative right here. So please pay attention to that. I just put a star by it. Okay, there's a negative right there, which means this is a negative. This is a positive. Mr. Shore's trying to fix stuff. I'll put stars by my fixes here. Okay. Trying to fix it all for you. Sorry about that. So there's a couple of mistakes. And that makes more sense. So this comes out to be a negative 0.5h plus, and then we have 67. But see, I caught my own mistake, and here's how I caught it. When I looked at my line, my graph here, I noticed it was sloped downwards. See how it's kind of going down? And then when I looked back at my function, I saw that I had a positive 0.5 for my slope. That didn't make any sense. So I did catch my mistake, and it's been fixed. So please correct your notes. Let's go back now and graph that thing. So to do that, we're not going to press stat plot. We're just going to press regular y equals. Okay? We're going to type this function in. We don't have an h button, so we'll just have to use x. So negative 0.5x plus 67 graph. Here comes our line. And now if you look at it, you realize, man, that is not a good fit of the data. That is not a good fit. And what happened on this was there were many months that I could have chosen from, and I chose, remember, to use August, and I think it was May, right? August and May. So let's go back and see why that might have been actually a bad choice. I used August and June, excuse me. August and June was a bad choice because I probably should have picked something closer to the beginning of the year and something towards the end of the year, and I picked two sort of toward the end of the year, you know. Well, one's in the middle of the year, one's later in the year. So probably not a good choice. So how do you know which to pick? The answer is you don't, and you don't need to know. We're going to actually get the calculator to draw a better line than this anyway. So the next part of this question is to find an equation of best fit. Okay? So the last part of this is use a graphing utility to find the linear function of best best fit, or you can just say the line of best fit. So this is the cool part. Now that you already have told the calculator the data, you can just ask the calculator for that equation. So let's go back to our calculator, and this is the magic part. My line is junk, so I'm going to go to y equals and just clear it out. That's garbage. And I'm going to go here to stat, and I'm going to go to calculations, C-A-L-C. It doesn't mean calculus, it means calculations. And if you look in the calculations menu, you'll see one that says linear regression AX plus B. This thing is so cool. All right? So if you go down to option 4, it's going to use for our lists L1 and L2, our X and our Y, lists X, sorry. For X, we're going to use list 1, and for Y, we're going to use list 2. Don't worry about frequency list, just leave that blank. Go here to store regression, and let's press variables. That was this button here, vars. Then scroll over one to where it says Y vars. See? And then choose function, enter, and 1. It's going to store our answer, the perfect equation here, as y1 in our calculator. So now I'm going to press calculate, and what it did is it gave me the equation of the line. Y equals ax plus b, where x is the humidity and y is the temperature, but a here is our slope. It's negative 2.09. Remember, I was using negative 0.5. What a horrible estimation, right? And the b, that's our y-intercept, that is 192.9. I was using 67. No wonder mine is so bad. Let's see how their graph compares in fitting the data compared to my graph. If you press y equals, you'll see it's already stored here for you. The calculator stored it under y1 equals. There it is, down to the nearest 10 billionths or something. All right? Super accurate. If you press graph now, check this out. Here comes this line. Look how well that thing fits the data. Now you might say, Mr. Shore, that didn't even touch a single point. You're right about that, but it did come through and do its best to touch all the points. So what's happening here is it's trying to stay as close to all the points as possible. And the calculator is doing what's called a regression. And it can do this with straight lines. It can do this with parabolas. And you might even say that, Mr. Shore, I'm not sure a straight line is the right way to compare humidity and temperature. And I would actually agree with you. I never said it was. I was just asking you for a linear function. But it doesn't mean it's the right linear function. Maybe the function shouldn't even be linear. Maybe this is a parabola. You know what I'm saying? Okay, but anyway, going back here, we can see our answer one more time. Remember, it was stat, calc, linear regression, and we planned to store the regression equation as variables, y variables, function y1, and when we pressed calculate, it gave us the a and the b. Bam. Very, very cool. Out pops our answer. Okay? Big wham-booey there. Bam. Now let's do one more thing. If you go to your catalog, that's second and 0. If you go down to the D's, or even faster, just press, see this little green D right here? Just press that. It'll jump down to the D's for you. Go down to diagnostic on, and press enter, and press enter again. Now that the diagnostics are on, when we run that stat calculation for linear regression again, it's going to give us more detail than before. Now it's giving us some other things, r squared and r. This r is important to us. R is always a number between -1 and +1. As you can see, the r is -0.93. The negative number just simply means that the line will be sloped downwards. The fact that 0.9 is so close to 1 means it's a very good fit, which we can see it really is. So all that remains is that we write our answer, and so we can just steal that from here. And we usually round to the nearest thousandth in the spirit of the AP exam. So I'm talking about AP Calc. Negative 2.092x. Well, why don't we write it in we were going to write T of H. So we have negative 2.092h minus, actually I think it was plus, let's go over here and see here. Yeah, it was plus 192.906, plus 192.906, and this is the linear function of best fit. Have a great weekend. Sorry I went over a little.